Magandang araw! I hope everyone who is watching this video is safe, healthy, and happy. Now, in this video, we will continue our discussion on nuclear chemistry. So this will be nuclear chemistry part 2, where we shall discuss about half-life. So in this video, we will describe what is meant by half-life and determine what factors affect half-life. We will calculate the amount of radioactive material that will remain after an integral number of half-lives. We shall calculate the age of a material based upon its half-life and describe how carbon-14 is used to determine the age of carbon-containing objects. Now, during natural radioactive decay, not all atoms of an element, it is common knowledge that not all atoms of an element are instantaneously changed to atoms of another element. Now, this decay process takes time, and there is value in being able to express the rate at which this process occurs. Normally, we use the concept of half-life. Now, in our discussion, we shall denote half-life by T sub 1/2. The half-life is the time required for half of the starting material to change or decay. So the half-life refers to the time that a particular quantity requires to reduce its initial value to half. So for example, initially we have 5 grams of a radioactive material. At the end of its half-life, the 5 gram will be 2.5 grams. So that's the concept of half-life. Yung panahon kung saan yung radioactive material ay magiging kalahati ng original amount niya. Alright, so we have here a graph which shows the disintegration of cobalt-60. So on the x-axis, you have the number of half-lives. On the y-axis, we have the percentage decomposition. So we start with 10 grams of cobalt-60, whose half-life is 5.27 years. So at the end of 5.27 years, so after one half-life, the 10 grams will be reduced to half. So we now have 5 grams of cobalt-60. So that's 50% of the original amount. At the end of the second half-life, so another half-life, another 5.27 years, the 5 grams will be halved. So it will now be 2.5 grams rather. So at the end of the fourth half-life, so the cobalt-60 will be reduced to 0.625 grams. So from 10 grams, it will be reduced to 0.625 grams. So that's how we describe or denote half-lives. Now, half-lives can be calculated from measurements on the change in mass of a nuclide and the time this change occurs. But the only thing that we know is that in the time of that substance half-life, half the original nuclei will disintegrate. Now, although we know that chemical changes can be altered by changing factors like temperature, concentration, and pressure in cases of gaseous reactants. For example, if we increase or decrease the temperature, increase or decrease the concentration, we can either speed up or slow down a chemical reaction, the rate of the chemical reaction. Any change on the factors mentioned could alter the rate of chemical change or chemical reaction. However, any of these factors do not have effect on the half-life. Each radioactive isotope has its own unique half-life that is independent of any of the factors mentioned. So on the table, we have selected half-lives of elements. So observe that uranium-238 has the longest half-life at 4.5 billion years, and carbon-16 has the shortest half-life at 740 milliseconds. Neptunium-240, which we shall use in our problem later on, has a half-life of 1 hour, whereas carbon-14 has a half-life of 5,730 years. I intended to show you a simulation of a disintegration of a radioactive material. However, this presentation cannot accommodate that. So perhaps some other time I'll be able to show you the simulation. So let's proceed directly to problem solving. So for our problem number 1, we have this. If the half-life of 100.0 grams of a radioactive isotope is 8 years, how many grams will remain in 32 years? So we are given a span of 32 years with a half-life of 8 years. So we must be able to determine how many half-lives are involved in the span of 32 years. So we divide 32 by 8, so we have 4. So it means that the isotope will undergo 4 half-lives. So we shall just provide a diagram, no, showing the 4 half-lives of the radioactive isotope. So we start with 100 grams. So after its first half-life, the 100 grams rather, will be reduced to 50 grams. Another half-life, the 50 grams will be reduced to half. So it will now be 25 grams. And after the third half-life, it will be 12.5 grams, and after the fourth half-life, half of the 12.5 grams will remain, which is 6.25. So after the 4 half-lives and after 32 years, the 100 grams radioactive isotope will be reduced to 6.25 grams. So we have another equation which relates the amount of material which remained after a half-life. So it's the product of the expression 1 over 2 raised to the n, where n is the number of half-lives and the other factor is the original mass. So we just have to multiply the two. Okay, so for example, we have this problem. If there are 60 grams of Neptunium-240, how much Neptunium-240 remains after 4 hours? From the table earlier, we observed that Neptunium has a half-life of 1 hour. So if we are given 4 hours, it means that this sample has undergone 4 half-lives. So the value of n is 4, referring to the 4 half-lives, not the 4 hours. So in the span of 4 hours, we have 4 half-lives. Thus, n equals 4. So we have this expression 1 over 2 raised to the 4th. So that is 16. So 1 over 16 times 60 grams. So we have 3.75 as the amount which remained from the original 60 grams of Neptunium-240 after 4 hours. Now, the radioactive half-life refers to the amount of time it takes for half of the original isotope to decay. So we have another equation which relates the mass of the radioactive material after a half-life or after a certain time interval. The mass of the original mass rather of the radioactive material, K, is the decay constant and T the time interval. Now, we have this problem. So what is the decay constant for a radioactive isotope with a half-life of 22.5 grams? So since this is a half-life, so the ratio n sub t over n sub o is simply 1 over 2. So we substitute that value to n sub t over n sub o and substitute 22.5 hours to our t and solve for k. And simple algebra would give us 0.0308 per hour as our decay constant. Now, let's proceed to another interesting topic, which is radioactive dating. Now, this is a process by which the approximate age of an object is determined using certain radioactive nuclides. In particular, if we use carbon-14, then the radioactive dating is called carbon-14 dating. Now, this carbon-14 dating is useful in determining the age of organic substances or organic materials. Now, as an assignment, I'd like you to read how carbon-14 is formed in the atmosphere for you to be able to appreciate better the the process, no, of carbon-14 dating, no? So as mentioned from the table earlier, the half-life of carbon-14 is 5,730. So the ratio between carbon-14 and carbon-12 in all living organisms remains constant, no, while the organism is alive. So literature says a ratio of 1:1 trillion. So 1 carbon-14 to 1 trillion carbon-12. So 1:1 times 10 to the 12, no? Okay, so we know that carbon-14 is the unstable one and carbon-12 is the more stable one. Okay, so when an organism dies, the consumption of carbon-14 is diminished, and therefore the ratio between carbon-14 and carbon-12 changes, no? So when we compare this ratio to the concentration, no, of carbon-14 and carbon-12 from any living organism, similar uh, organic material, okay, then we will be able to determine the or estimate the age of that organism. So we use this equation to solve for uh, the age, no, the approximate age of an organic material. So T, which is the age, is equal to the product, no, of these two expressions, T sub 1/2, which is the half-life, and the expression Ln, quantity n sub F upon n sub O, divided by negative 0.693, where the quantity n sub F over n sub O is the percent of carbon-14 in the sample compared to the amount in living tissue. So for example, if a fossil had 10% carbon-14 compared to a living sample, then that fossil would be, so what is the approximate age? So we just substitute the value 10% to the expression, no, the ratio n sub F over n sub O. So, and then the half-life of 5,730 of carbon-14. Simple algebra would give us an, an approximate age of 19,042 years old. So, almost 20,000 years old yung fossil na nakita natin. Now, although carbon-14 dating is useful, no, in approximating age of organic materials, it has its own limitations, no? So samples on the range of 100 to 50,000 years old can be approximated. However, lower than 100 or beyond, no, 50,000, we will have difficulty because by then the amount of carbon 14, no, is too little, no, too minimal to be detected. Another thing, substances must contain, no, carbon-14 or must obtain carbon-14 from the environment. And for this reason, aquatic samples cannot be effectively carbon-14 dated, no, because they are not exposed in the atmosphere. Therefore, very limited absorption of carbon-14. Lastly, accuracy of carbon-14 dating has been affected by atmosphere nuclear weapons testing because of hydrogen bomb, atomic bomb during World War II. There are many artificial carbon-14 in the environment, and this would increase, no, the amount of carbon-14 ingested by the organic material, and that would render our approximation very inaccurate. Alright, so that's it for our half-life. So these are the references if you want to read some more. I hope you have learned something about half-life and uh, is able to develop an appreciation of your knowledge on this so that you will be more wary, no, more careful and more discerning of uh, radioactive substances. Thank you so much, and I'll see you next time. Stay safe